It is a pleasure, of course, to present to you again on a presentation for sensing, preparing, modelling and affecting the battlefield with the applications of AI under a conditional constraint model for mission threat detection. The motivation about this is to be able to communicate to industry and partners how we can communicate a common understanding towards parts of the AI framework which might form an architecture as a basis for microservices and agents such that we're able to work together under a common framework. And what we want to do is support autonomy and decision making under that framework and to support integration and a common understanding between software and even humans. And that breaks down between an area which is really ISR and target acquisition in this case. So that's ISTAR as a summary. What we want to be able to do in our problem area is to be able to make decisions that are faster and more reliable and to develop representation formats for applications rather than having an idea for AI always been stifled about not having data. Actually, the challenge really is about creating effective representations and then converting data to that representations. And that is in actual fact the way in which you enable AI in capabilities. And so what we want to be able to do is also think about examples that we have already, which are like text to image, image to text, categorization at the edge, and data sets with record infill and video processing, and also the way in which we structure data. To be honest, the data that we talk about and the revolution that goes with that data is less about AI and more about data representations. That's actually what's become more prevalent in this time. It's not a high thinking machine or a decision assistance, but actually it's more complex processing with frameworks that make it easier to manipulate it with large memory models and data that allow us to do it at scale. And that is the real revolution, is not AI, it is data representation. And that's why the prevalence is for data science, not necessarily for AI. If we do look at AI and we look at those data representation and frameworks that go together, then we can categorize those into three areas. And when we look harder at that, we can think about the symbolic AIs as being more able to be understood by human, as they were constructed by human, less able to machine learn. And the ML side, more able to machine learn, less able to be understood by human. And inside, we can get this optimizing sort of approach using evolutionary algorithms, which might give us a solution, but it's not the most optimal solution. It is one that fits the fitness landscape. And so, as we go forward from that, that brings us an emphasis as we try and connect those two things together called neurosymbolic AI. And that may actually offer us design assistance and all sorts of wonderful features through what we call AI, which is really actually complex data representations to be able to machine learn something and understand it as an output. And that becomes a design assistance. So you can imagine the phrase designed with AI rather than incorporating AI. So the area of constraint models exist in project management, and they are really like influences that allow us to make decisions more effectively. So you could imagine cost, quality, time, and in some markets you might precedence some of them and one may suffer. In machine learning, we use conditional constraint models, hence that's in the title, and they're actually what they do is they take the machine learning model and they constrain the outputs to be within valid tolerances, and that's a way in which we can ensure safety. And so that's kind of what we think. When we think in EW about constraint models, we're actually thinking about models that constrain our thinking or assist our decision making. And we can see those in OODA loop, in the kill chains, and also in the Intel lifecycle. And I've actually always been interested in this area. And so we can take the OODA loop and the OODA loop process, as it were. One is actually a more complex form of the other, and the other really just talks about data dependency as a more elegant solution. And we can see that also in machine learning. That brings us to think about, with the Intel lifecycle, we can think that as being a precedence of where the data came from, and also the processes that went for that. which we term data lineage. Okay, and I've also been interested in this area from even my early days, thinking about the influences that affect a countermeasure and countermeasures language, and how we construct those along a kill chain constraint model in a onion of protection, such that each kill chain stage represents an intention which must be countered, and therefore it forms a framework for constructing a counter action. And the kill chain element to this has been quite important to me, and that of course is just one example of a constraint model. It could be avoid, evade, defeat, it could be many others, but this particular one we're going to center on. And the one that I'm particularly interested that's come here, or the most famous one, is the Rudd-Orthner F2 T2 EA, which is find, fix, track, target, engage, and assess. But the one that I had actually been using in my past when I was thinking along these trains was actually F2 RTEPE. And that one's find, fix, recognize, track, engage, prosecute, and effect. And that's because the way in which I had been thinking about this was making a prediction of where I felt that an aggressor had me in their kill chain, rather than Ronald Fogelman, which was how you had put something into a kill chain storage process. What we'd actually really like to do is fuse the two things such that our notion of a kill chain is applicable to both the prediction and even our own. And of course, it's got to be better if our prediction could match our own idea of a kill chain, our own targeting. And thus we have the F2 right ped. And what we've done is we've taken the recognized part of the Rudd-Orthner, and we've taken the assess stage of the Ronald Fogelman, and then we've added an identification stage just to complete the picture. So what we want to do is when we're thinking about those kill chains, and we can think about those, these are those intentions. And what we want to do about these intentions is we want to be able to make an observation which is evidence against that conservation, against that intention. And what we do is we observe something which is an engagement tactic. And what I mean by that is sometimes with the weapon system, there are many ways of operating that weapon system to get an effect. It could be that they're using the visual system with the laser ranger. It could be that they're using the radar. There are forms of this. What we want to do is form those evidence and say what all the possible intentions are for that evidence, take things that come before and will come after to down select what intention we think we are and where we think we might be in the kill chain. And so what we do is we find that there is a mapping of the engagement tactic relative to an intention step, which is part of a mission thread. And those mission threads might be part of a campaign aim, like preparing, sensing, modeling, effecting. Kind of like a bigger OODA loop type or engagement type warfare. And they might relate to a war plan. And where we go back to our, if we now have an idea about that coming to the war plan, something coming to the mission thread, that might make us think, therefore, have a confidence about the intention step and how we would counter that intention. And that gives us an idea about how we might do something about forming a counter strategy. So that's kind of like forming a countermeasure that both wins the war and wins the battle. That therefore relies on some key components. And those key components are the things that might be there to enable us. And we talked about some, at least two of these last year. One of those was a high disambiguation approach to categorization for ELAND. And we were able to separate 14 radar known ambiguous problem with 98. We actually got that down to 100, and we're now extending the data set even wider. Okay, we're trying to do that wideband and do that more effective and produce that, develop that work. The other part was that information is often incomplete, and what we need to do is infill data based on more observable things giving rise to less observable things. And we also showed last year that there was a knowledge-based approach in order to be able to complete information in database records using a structure that inherited and preserved data lineage. And we had that almost neural network approach, but provable in a provable method. Okay. And then this year, I've been looking at using auction algorithms along the kill chain stage in order to be able to do optimal tactic and effector selection. And that maps on to the subject area of kill web and mosaic warfare. So what we're trying to do here, as it says start here, we have some signals that we observe. We can see that those are some kind of tactic, classify those as that. And then what we will try to do is map to all the possible intentions that could be, possible intention steps that could be. And then what we could do is then we try and make that to identify or down select the number of mission threads and which campaign name that agrees to, and then make a counter intention. We do this cyclically as we appear to look at, say, almost like mode lines between our search, acquire, targeting, tracking, engaging type approach of the kill chain. And that helps us to be able to make an approach that is therefore robust and gets perfected iteratively, almost like the order loop, because we're continuing to observe, perfecting our idea and perfecting our orientation. And that is the loop that's going on. If we describe that as some kind of architecture to build, then what we can imagine is that in green are the kind of things that already exist, like the influences of OSINT, ELINT, and SIGINT, and data repositories coming together, and outputs for the common operating picture are data storage and information exchange, and our mission data outputs. And we're going to add these things in red for that expert system to complete data such that records can be used more quickly. The synthetic data setter generator that we talked about last year that enabled us to do the high levels of disambiguation, and flirting that between real data and recorded artifacts of data, of real data, mixing those into a sort of model form for doing the GAN approach, to be able to mix those things together, to be able to make model updates, and then also to make an ELINT categorization model, and then supporting our little loops that we just described. Along with that, we would have those effects for synchronization, or to be able to take and make a counter intention and to be able to play those in some way and make an effect approach to that. This brings us on to the area of kill webs, and kill webs basically are an idea to think about kill chains as being non-linear, as actually as networks. And when you say there are networks, it's actually a bit more complicated. They have selectable options that are possible, and they observe maybe more possibilities within them. And what we actually are doing here is, in our context, is we're linearizing kill chains to make a recognition to identify both the kill chain stage and the campaign name through thread detection. And that brings us on to the next element, which is to consider that if we do that and we just consider not just machine learning the ELINT and machine learning the stages, but to machine learn the patterns, and that sounds like the equivalent of doing the imagery equivalent of posture detection. If you're familiar with that, it's like when you take an image and you sort of like see almost like the skeleton and it says, oh, he's throwing something. That posture detection, do the ELINT on that in terms of behavior of something scanned me, something is improving its tracking, something is trying to now send something and guide something, then that sort of area of that we can do in a generic form. From lots of examples of that we know to predict one that we haven't seen yet. And that's the area of generic threat. And that helps us along what we can term as mosaic warfare, where different items are put together for a kill chain ad hocly in order to achieve a threat intention. So hopefully that was interesting to you.